Okay, let's begin this week's online lecture. Now, in this week, we will study chapter 31, and the title is Electromagnetic Oscillations. Okay, let's review first. In the last lecture, we learned the Faraday's law of magnetic induction. We learned how to express it using the EMF and also by using the electric field, right? Okay. And then we also learned the Lenz's law, which explained the negative sign in the Faraday's law. And basically, the Lenz's law showed us that the nature doesn't like the change. Okay, so it tries to oppose the change, so that's why we have the negative sign. Okay, and then we also learned the inductor, which is just a coil, and its property known as inductance. So, and in this device called inductor, basically, when it's included in electric circuit, it opposes abrupt changes in current. Okay, and then we also learned, as a result, how current changes with time in RL circuits with resistor and an inductor. Okay, and then we also learned how energy is stored in a magnetic field of an inductor. Okay, so far we have learned the electricity and magnetism, and in doing so we already have seen a little bit how these two are connected to each other, and from now on in this lecture we will really see how these two are connected to each other and try to combine them. So first we will see how current oscillates in currents with both inductor and a capacitor. This inductor represents the magnetic field and capacitor represents the electric field. Okay, so they are together, so they will get combined. And then we will actually see how these oscillations in circuits is similar to the mechanical oscillations that we have learned in the spring semester. Okay, mechanical oscillations mean the spring plus mass. Okay, and then we will also learn how this current and potential changes with time when we have RLC circuit. Okay, now in the circuit including inductor and capacitor, we add the resistor and see how it goes. And then finally we will also learn how power transformer works. Okay. So we begin this chapter by reviewing the RC and RL circuits. Okay, you know, here R is the resistor, and in any real circuit there will be some resistance. So therefore we always have a resistor there. And previously we studied the two different cases. First with resistor and a capacitor, which was RC circuit, and a resistor and an inductor, and it was RL circuit. Okay, and in RC circuit we learned that the current flowed only for a short period of time after the switch was turned on. Why was that? Because this capacitor has a gap through which the charges cannot flow. So therefore the current flowed only during the short period of time during which this capacitor was charged or discharged. Okay, and when it was charged up to an amount of charge Q, the energy stored in this capacitor was written this way, and then if you divide this energy by the volume of the capacitor, and then the energy density was proportional to the square of the electric field, right? That's why we say this capacitor stores energy in the form of electric field. Okay, and in contrast, in RL circuits, the current increased from 0 and became saturated after some time, right? Why was that? Because being saturated means that it will flow at constant rate, because this inductor is just a wire and it's only wound in the form of a coil. So after everything is done, the current will just continue to flow. But in the beginning, because of this self-induction process, the current cannot immediately go from 0 to a large value. So it was increasing slowly, right? Okay. And when the current of I is flowing finally, the energy stored in this inductor was written this way. And then if you divide this energy by the volume of the inductor, its energy density was proportional to the square of the magnetic field. So that's why we say inductor stores energy in the form of magnetic field. Okay, so we studied these two cases separately. But then what if you directly connect capacitor and inductor against each other? Okay, these are the examples of capacitor and these are the examples of inductor. So we will see what happens when you have these together. So first we will think about the case without resistor, and then later we will add the resistor. Okay. So how do we see that? Okay, we will again use this similarity experiment. Okay, here we have an inductor and a capacitor and a battery, and here we also have a resistor, and then we will see what's going to happen when you actually turn on this switch. Okay, here again we have this circuit with inductor and a capacitor and battery to charge the capacitor and 3 switches. Okay, and in fact I already said that we will consider resistance later, but why do we have the resistor here? Well, in fact, if you don't have a resistor here, then when you try to charge the capacitor, the amount of current will be infinite, so that's not going to work. So we inserted the resistor here for the time being, but eventually when we try to observe the oscillation, we will actually remove this. So let me first try to charge the capacitor. In order to do that, I have to close it. Okay, and then close it. Okay, nothing's going on because I didn't actually start the time. So this, by pressing this, now current will flow in. Okay, you see that the electrons are moving. So on this side is red color, which is positive, and the blue color negative. So it's charged, right? Okay. And then I will disconnect this. Oh, disconnect this switch. Okay. So and then charge is not moving because actually it's disconnected on both sides. So okay, now it's fully charged now. Okay. And then if I close this switch, now the current will start to flow into the inductor, and then we will see what will happen. Okay, and in fact, in doing so, what we want to know is how current and voltage changes with time. So let's use this current chart. Okay, so this is actually a graph which shows the current as a function of time. So I will connect to it to here. Okay, and then it's showing the current. Right now, its current is 0, right? Okay. And we also have this voltage chart. Okay, voltage chart has 2 knobs or 2 electrodes, so you can check the voltage potential difference across certain 2 ends. So I will put it over here, and this guy here, and it will show the potential difference across this capacitor, right? Okay, right now it's about 10 volt. Okay, so I will change the scale so you can see it more clearly, maybe up to here. Okay, and then this guy also, actually as a preparation, I will also change the scale. Right now the voltage is like almost 9 volt and current is 0. Okay, and then we will see what will happen if I actually close this switch, and then also take a look at what it will be happening here. Okay, alright. In the beginning, looks like nothing's much changing, but you can immediately see current starts to increase and voltage starts to decrease, right? Okay, and then you can see that, okay, now current, the charges have changed its polarities. It's positive on the left side and negative on the right side, and then voltage became negative. Okay, and then it's coming back. Okay, the current now actually going to the negative side, and let's expand it more to see it more clearly. Okay, so can you see it's actually now voltage has come back to positive, so the right side is again a red color, and at the same time the current is coming back to plus side. Okay, so these curves look like they are sine curves, or sine or cosine, right? and they continue to change. And then here you can see that when the current is maximum, voltage is 0. Okay, and then when the current is 0, voltage is like negative minimum, or you can also say the amplitude is maximum. And when the current becomes negative, again, the current becomes minimum, again the voltage becomes 0. And then when the current goes back to 0, then voltage becomes maximum. Okay, it's just like the relationship between sine and cosine curves, right? Okay, this is actually what is happening. Okay. So, and then we will try to explain what is actually going on. And then, well, in a nutshell, why this happens is because when current wants to flow out of this capacitor, it cannot immediately change, so it just continuously, gradually change because of this inductor. Okay, that's what's going on. So let me explain what we have seen in the simulated experiments step by step. Okay, so this is the first step. In the beginning, we have the capacitor fully charged, but there is no current flowing yet. So therefore, inside the capacitor, there is a maximum amount of charge and also the maximum strength of electric field. So therefore, it has the maximum amount of electric energy. But since there is no current, there is no magnetic energy in the inductor. Okay, and when the time flows, now the charge starts to move out. So therefore, the current flows counterclockwise, right? Here, like counterclockwise. And then amount of charge in the capacitor has been reduced. So therefore, electric field has also been reduced. And the current starts to flow, and this amount of current will increase, right? And then there will be electric energy in the capacitor and also the magnetic energy in the inductor. Okay, and then if you wait long enough, now amount of current will continue to increase, and all the charges would have been discharged from the capacitor, right? Okay, and then since there is no charge in the capacitor, one might think that there is no more current to be flown. But because of the inductor, the amount of current cannot immediately drop to 0. It will only decrease very slowly, right? Okay. And then at this moment, but what you have to think about is that since there is no charge in the capacitor, no electric field, so therefore no electric energy in the capacitor. But the inductor has the maximum amount of current, so therefore there will be the maximum amount of energy in the inductor. Okay, and then of course, just like I said, the amount of current has to decrease. So therefore, if you wait a little bit more, the current has been reduced, and then now the charge starts to accumulate on the opposite side of the capacitor. So therefore, electric field starts to appear, and at this moment there is both current and charge. So therefore, there is an energy on both devices. And then if you wait again long enough, now current will come back down to 0. There is no current, and all the charges would have been accumulated on the other side of the capacitor. Okay, at this moment, there is a maximum amount of charge and the maximum strength of electric field, but the direction of electric field is opposite with respect to the initial case. Okay, but then the electric energy does not depend on the sign of the electric field, so therefore the electric energy now has again become maximum, and since there is no current, there is no magnetic energy in the inductor, right? Okay, now we have come to this case, and again because of this because of this electric field, now again this charge has to flow out of the capacitor, now this time clockwise, which is opposite with respect to the initial case. And then what is now going on from this moment is actually exactly the same with the first case, except that now the polarity is opposite. Okay, so now instead of counterclockwise in the beginning, now the current is flowing out clockwise, but everything looks the same. And if you wait some time, again the amount of charge has been reduced in the capacitor, and then the size of the current has increased a little bit, but the direction is, as you can see, is opposite with respect to the initial case. And again, there is again a moment when the capacitor is fully discharged, and then the current has reached its maximum. And then again, the charges will again accumulate on the other side of the capacitor, and then the system will continue to go through this process all over again. Okay, so during this process, this is basically a repetition, and you can also call it an oscillation because it moves back and forth between the electric energy and magnetic energy.